Just try it. Chonchubhair. You're fine. Okay, can you hear me with this? Yeah? Okay, cool. Thanks. So hi everyone, my name is Deirdre Chonchubhair. I am a PhD student at the University of Galway in Ireland. My supervisor is Dr. Aaron Golden, and today I'm going to talk a little bit about multi-wavelength observations of the flare star binary system, EQPEG. Is anything going to change it?
No.
Nope. It's changing it on this one.
Oh.
Now maybe just click there and it should work. No. Yeah. Yeah, you can just do it like that. Fine. If it works. Yeah. Okay, cool. Thanks. Yeah, so the background and motivation for this work was in 2017, the detection of polarized coherent flares from the flare star UV SETI using MWA at 154 megahertz, which strongly indicated the presence of auroral currents within an extensive magnetosphere, which was unexpected for an M5.5 dwarf. So my supervisor came up with this proposal to look at EQPEG in, first of all, in low frequency radio to try and confirm the presence of coherent emission. And this passed on in other M dwarf flare stars. And secondly, to see if the origin, if it was present with this electron cyclotron maser instability, and then using high frequency radio and optical observations to try to link the radio and optical emission, and so the surface and coronal flare to auroral activities. So then we've seen this plot a couple of times already today, which is for looking for CMEs. First of all, one way to find them is you'd see this EUV dimming. The next one is a prominence eruption. The third one is the low frequency radio, that you'd see this distinctive sweeping pattern, and that's a signature of the CME propagating through space. And then the last one is a white light coronagraph. See will this work this time? There we go. Oh, now I've gone too far. Okay. So EQPEG itself, it's an M dwarf flare star binary system. It's at a distance of 6.25 parsecs, a separation of 5.8 arc seconds. For EQPEG A, it's an M3.5. It has a rotation period of just over a day and a magnetic field strength of 480 Gauss. And for EQPEG B, it's an M4.5. It has a rotation period of 0.4 days and a magnetic field strength of 450 Gauss. We know that the known flare rate in the U is we expect 1 flare per hour above 5 × 10⁻30 ergs. And there's also been a recently detected exoplanet around EQPEG A with a mass of 2.3 times Jupiter mass, but it's outside the habitable zone. So for our observation campaign, we had simultaneous observations in 2018. The first one was with the Liverpool telescope, which is an optical 2-meter fully robotic optical telescope in La Palma, and we were using the IOO photometer in the SCSSU band. We have 6.7 hours of observations at a 20-second time resolution. The next one is the high frequency radio. So that was using eMerlin, the set of 7 radio telescopes spread throughout the UK. We were looking in the C band, so 4.8 to 5.33 gigahertz. We have 11 and a half-ish hours of observations with that. And then the last one was LOFAR. So just, if anyone hasn't seen a LOFAR station before, that's just one station. But this was actually with the International LOFAR telescope at using the HBA at 110 to 190 megahertz. But unfortunately, the following day, we got this email. My supervisor got this email saying that there was problems with the stations and none of the LOFAR data was actually taken. Yeah, heartbreaking. But what do we have? Let's go what we have. We still have the optical and we still have the high frequency radio. So with this, we're going to try to provide information on the coronal environment. We're going to look at the optical flares and their association with coronal radio emission at gigahertz bands. We can't directly detect a CME, but we can try to constrain its likelihood and look at EQPEG's magnetic activity. Okay, so these are some of our results for EQPEG A in the optical. So these have been biased and flat fielded, and then used source extractor to get a time series, and then corrected that using the comparison stars, and then found these flares by eye. So numbers 1 to 5 there. And we have both classical and complex flares, and then using the equivalent duration, worked out the energy. So the energy for F4 and F5 are 2.7 by 10 to the 31 ergs and 1.4 by 10 to the 31 ergs. And then we did use the same method on EQPEG B, and these are the flares that we observed with that, and the energies are up to 5.8 by 10 to the 30 ergs. Pressing the wrong one. So how can we use this to constrain a likely CME event? Well, the proposed threshold for a solar flare to have an accompanying CME, when we apply that to the stellar case, is this 8.38 by 10 to the 29 ergs in SDSSU band. So using that, our data suggests that all of our observed flares should have been above this threshold. But how do we actually detect a CME? Well, ideally LOFAR, but let's have a look at our high frequency radio instead. So the top panel is the optical for EQPEG A, and then these bottom two panels are the radio. So we have Stokes I in the middle, and so the flux, and then Stokes V, the circular polarization in the bottom. And so these they've gone through the eMerlin data reduction pipeline, and then they've been cleaned using CASA. And then when we looked at the raw I and V data, there was just quiescent, there was nothing to be seen. So we binned it up. These are binned into about 15-minute chunks. And so if you look at F4 here, and then following that, there's this bump in the I, and then corresponding with that is a flip in the polarization. And you can see kind of the same thing for F1 as well. You have a smaller bump here and another flip in the polarization. This here is about 1 millijansky. And then there was no detection of EQPEG B in the radio data. So can we use this to put some constraints on likely CME events? So if it was a type 2 burst, we would expect to see this low frequency in tens of megahertz in the LOFAR, but we don't have that, so we can't say that. And then if it was a type 4 burst at gigahertz passband, we'd expect to see something like this. So this is actually for Proxima, and down here is the optical flare, and then this panel is radio. So you can see there's a corresponding radio burst, and then following that, there's two longer with a more complex morphology bursts. We don't see any of that. We don't see an initial flare in the radio, and what we do see is slower as well. So it's more likely to be gyrosynchrotron emission coming from an involving magnetic region. Pressing the wrong one. So then we wanted to check if our flares were consistent with any other flares. So we had a look in the test archive, and this is one sector of test data from I think 2022, and it's been, so the black is the test data that's been calibrated, and then the red are these flares that have been found using Altipony. So it found about 150 flares in this one sector of data. This is the 20-second test data as well. And then the last thing we've done so far is look at these flare frequency distributions. So the black dots are tests, and then the green is EQPEG A, and the blue is EQPEG B. And you can see that they are, it did seem to be following the same pattern. This is a preliminary result because I'm not 100% sure if it's the correct way or if there's a better way to plot this, because tests only sees EQPEG, the system as a whole, whereas I can see each A and B. So it'd be nice to talk to someone after it. If anyone has any ideas, I'd love to hear them. And then our conclusions. So from our optical data, we expect to have several candidates for CMEs for both each A and B. Each A in the radio, is it a type 2 burst? No, we can't say that. Is it a type 4 burst? No, it's we see slower. We've no initial burst. So it's most likely gyrosynchrotron emission from an evolving magnetic region. Our data is consistent with the test data. And the last thing is just, I think we need, like everyone's kind of said it already today, but we need more multi-wavelength simultaneous campaigns, including these low frequency observatories, especially with a lot of these are getting updates on these days. So like LOFAR is having its update, OBRO is about to come online, and then obviously the SKA is on the way. So I think they're important to try to detect stellar CMEs. So, and just thank you for listening, and thank you to the organizers. I'm actually not sure. I'm still working on that at the moment, but yeah, that's coming soon.
Yeah, did you, it's hard to tell from the plot, but
Yeah.
were the stairs B and stairs I, or is it, what was the degree of circular orientation?
Oh yeah, sorry, it's really small on that. So it's point, it goes up. Where's my pointer? So here's 0.5 millijanskis.
Okay, so what's the over I?
Oh, I don't know. I haven't worked that out. I can't do it right now. I'll come back to you.
All right.
Sorry, can you start to say it again? Can you see negative radio bursts in the frequencies? Is that it? I don't know. I'd never heard of that until Rachel's talk earlier. So
any other question? Okay, thank you.
thanks.
So we okay, we have about 27 minutes, and so we would like to ask all speakers to come here